Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. In today's video, we are going to explore various phenomena in the atmosphere associated with the color of light and particularly scattering of light. We will examine why is the sky blue, yet if we look towards the horizon, it is less blue, it is more whitish. We will examine why is the sun yellow or red when we look at it from the surface, but if we look at it from above the atmosphere, then it appears white. We will also talk about white moon and white stars in the evening. And of course, we will also explain why are the clouds white and yet sometimes dark. So let us first examine why is the sky blue. Everybody should know this. Here is the surface of the earth, but let's not make it yellow, let's make it black. Here is the surface of the earth, and here is the sun. Nothing in this figure, of course, is to scale. Sun shines in all directions. And now here is our eyes looking above us. So we are not examining the case when we look towards the sun. We look above us over here. Well, all we need to know is explained in previous lectures, and particularly lecture on the scattering of light. We know that scattering of light of molecules and atoms in the atmosphere is dominated by the regime of Rayleigh scattering. And in this regime of Rayleigh scattering, we know that scattering is proportional to 1 divided lambda to power 4, where lambda is wavelength of light. And we know that the shortest wavelengths, which therefore will be mostly scattered, are blue and purple. So we will have a lot of blue light being scattered of this molecule. And because red and yellow are much longer wavelengths, we will once in a while only have yellow, green, and so on. And a lot of purple light also. So you see, when you look at all these colors, the sky appears to be blue. Appears to be blue exclusively because of Rayleigh scattering. It is very important to understand here that that the sky is not blue because of chemical composition of the atmosphere. It is blue because atoms and molecules in the atmosphere are much, much smaller than the wavelength of visible light. In other words, if you are in the atmosphere of some distant planet, and that atmosphere maybe has different molecules and atoms in the atmosphere, but they are much smaller than the wavelength of visible light, that atmosphere would also be blue. It has nothing to do with chemistry. As you can see, blue light scatters mostly, and therefore we see that the sky is blue. Now, few notes. Because once in a while other colors, namely yellow, green, red, will also scatter, that means that the sky is not perfect blue color. It is very blue, but not perfect blue. Other question that we need to examine is why the sky is not purple, because purple is even shorter wavelength than yellow, and because of that shorter wavelength than blue, and because of this relationship, then we should expect sky to be purple. Research suggests there are two reasons why the sky is not purple when we observe it. First has to do with physiology of our eyes and brains. Medical research suggests that our eyes are much more susceptible to blue color than purple color. So if we have equal amount of purple and blue, we tend to see more blue than purple. Other reason, you will remember that the electromagnetic spectrum of solar radiation is such that purple color is less dominant than blue color in electromagnetic spectrum. In other words, the sun sends more blue color than purple color. So although purple color tends to scatter more, there is less to scatter to begin with than blue color. And all combined, we see sky blue. Now we can leave this here, and that will also explain to us why the sun quite often appears to be yellow. This over here is yellow, very difficult to read. So why would sun appear yellow? Well, it would appear yellow because you see, if there are, and there are of course, molecules and atoms between the sun and our eyes, then these molecules and atoms, as we just discussed, will scatter blue light. Of course, sometimes they will scatter it forward, but they will scatter it back in any given direction. So there will be a lot of scattering of blue light. And consequently, the light that directly passes to our eyes is yellow, red, green. Green is also shorter wavelength than yellow and red, so it will scatter more. So in other words, yellow and red will predominantly survive, and therefore when we observe now the sun, we look in this direction, you can see that combination of these colors results in reddish, yellowish sun. But if we are in the outer space now, if we are levitating in the outer space and we observe the sun, of course you should never ever look directly in the sun, but we observe the sun from outer space, then it will appear to be white. Why white? White because there is no atmosphere to scatter any light. So we are receiving full electromagnetic spectrum from the sun. In other words, all colors are present, and combination of all colors results in white color, and that is why the sun appears white and yet red or yellow if we are looking at it from the surface of the earth. And lastly, I said if you look directly up, the sky is blue, or you look in this direction, it is blue, or you look in this direction, it is blue. If you look into the sun, then you see it yellow, red, sometimes also a little bit white. But the question is why, when we look horizontally towards the horizon, the sky is less blue? Why is sky less blue in the horizon than above us? To explain that, we have to now invoke knowledge from my lecture on the density of the atmosphere, of the air in the atmosphere, and how density changes with height. So let us examine that here. We know if these are molecules and atoms of air, we know the density of air exponentially decreases with the height. So as we are moving away from the surface, there is less and less atoms and molecules of air. And there are many, many of them close to the surface. So look at this now. First, you look up. This arrow indicates where you look. You can see that the light that is coming from sun in this part of the atmosphere typically travels unobstructed because there are only few molecules and atoms that will scatter the light. So most of the scattering will happen here in the first 5-10 kilometers above you. So most of the scattering, as I just said, happens here, where the density is high. And therefore, the light that scatters perhaps only once. So let's say the white, the light comes in and then maybe scatter once. It is very likely that that will be blue scattering, because we just said scattering is proportional to 1 over lambda to power 4. It is very likely that the scattering will be blue, because there are only 1 to 2 scattering events before maybe light comes into your eyes. However, when you look horizontally in this direction, you will kindly notice that you are looking through very, very dense part of the atmosphere to the long distance over there. And there are many scattering events that are occurring because persistently density of the atmosphere is high. So the light that is coming from this direction is encountering many, many molecules and atoms. And of course, blue light is scattering a lot. Now, first of all, if you look in the distance, blue light is first to scatter, so there is less and less blue light to scatter. Now, some of the light that is coming from this direction, again, it's more likely to be blue. But because there are so many molecules and atoms to scatter light, although the blue light is more likely to be scattered, there are so many occasions in which yellow light will be scattered, as well as red light, as well as green light. And then when you combine all this, you see that dominance of blue color is lost compared to when you look directly up. And that's the consequence, as you can see, of very high density of the air close to the surface and many scattering events that are happening here, whereas when you look up, atmosphere is only dense in the first approximately 10 or so kilometers, so there are only few scattering events that can happen. And because there are only few scattering events that can happen, then it is much more likely that the blue light is the one that will scatter. The next thing that we can also simply explain here is why the moon is white, as well as distant stars appear to be white. In fact, this has little to do with the property of light. This has more to do with the physiology of our eyes. There are two types of receptors of light in our eyes, and one type are called rods, another cones. Now, cones, we have less cones, but they are very susceptible to light, and particularly those receptors are the ones that can distinguish color. And cones are affected by light that is coming predominantly directly in our eyes. Whereas rods, we have much more rods, but they cannot, or they are not very good at distinguishing different colors. So the light that is coming from the side is typically received by rods. And you can now do a simple check. When you look directly, wherever you are looking, I'm looking into camera, I can distinguish all colors. But the peripheral light that is coming into your eyes, notice that you have difficulties distinguishing light, that color of light that is coming from the side. Rods are also receptors that are active when we have a low intensity light. And this is the key why the moon is white and why the distant stars are white. I will repeat, when we have a low intensity light, rods receptors dominate over cones. And as I just said, rods cannot distinguish different colors. So if you have faint light, that light will almost always appear as white because rods cannot distinguish different colors. You can also test this. When you wake up in the middle of the night and it's dark, but not pitch dark, so you can still see a little bit, you notice that you do not distinguish colors. When you open your eyes in the middle of the night in your bed, check that flower or plant in your room, and you will see that you do not properly see the color. Of course, you see the plant, but you do not see color of the plant. And that's because the light is so faint that the cones are not activated and you're using rods. But rods are not good at distinguishing color, and therefore you see it black and white. And that's why the moon and the distant stars are white. You see, when the moon is full, when it's the most bright, it is still approximately 400,000 times less bright than the sun. So very little light comes into our eyes. And the last thing to discuss here is, why is the sky sometimes red? To discuss why is the sky red, we have to look into the geometry of our planet Earth and the distant sun that is here. And the sun is shining in all directions. Once again, nothing here is to scale. This is the surface of the Earth, and this is the atmosphere above the Earth. And here you are, small x. Now, during the sunset or sunrise, you can see that this is the distance that the light needs to travel through the atmosphere to reach your eye. Whereas in the middle of the day, when the sun is perhaps here, this is the distance that the sun ray needs to travel before reaching your eye. So this is during the day, this is sunrise or sunset. In other words, you can see that the distance that the sun ray travels during sunrise or sunset is much, much larger, travels through the atmosphere, is much larger than during the day. And now, because again, we know that scattering S is proportional to 1 over lambda to power 4. In other words, short wavelengths will scatter more than long wavelengths. Well, the blue light is the first to scatter. And it is scattering here. And all blue light will scatter. So the only light that survives is red and yellow. And consequently, as well as a little bit of green. And consequently, what you see is red, yellowish sun, because all blue light scattered here. Whereas when the sun is above your head and you look at it, well, as we just discussed a few minutes ago, density of the air here is only high close to the surface. So the light that will scatter is this blue light that in the case of sun having low angle scattered over here. So kindly note that even when the sun is setting or rising, when you look directly into sun, it is red. But if you look at the sky above you or under some angle, it is still blue. It is still blue because you're observing this light ray that reached here, top of the atmosphere, and then scattered into your eyes as a blue color. Because once again, this is a short distance that the sun ray is traveling through the atmosphere, and the likelihood of blue scattering is high compared to the likelihood of yellow or red scattering. And that explains why the sun is yellow or red during sunset. And lastly, why are the clouds white? So if we have a cloud, well, let me erase this and then I'll explain it. Here is the surface of the Earth, and here is a nice cloud that appears to be white. Why is it white, whereas the sky is blue? And that has to do now with different regime of scattering, and that's Mie scattering. You will remember that in Mie scattering, and Mie scattering, let's say S scattering, happens when the size of the particles that are scattering light is similar to the wavelength of light. So in clouds, we have small droplets of water. And these droplets of water can be similar in size to the wavelength of visible light. And in these cases, you will remember from my previous video, all colors are equally likely to scatter. In other words, when we have Mie scattering, all colors are equally likely. So blue, red, green, yellow, purple are all equally likely to scatter. And combination of all colors is white. That is why clouds appear white, because they scatter in Mie regime that does not favor any wavelength. All wavelengths are equally scattered, and combination of all light therefore is white. However, if we have cloud that is very, very thick, and we look at it. So here we are looking at this cloud. It appears to be dark. Why is that? Well, that's because light that reached this cloud is now being absorbed in the cloud. The cloud is too thick that the scattering is diminishing as the thickness is increasing, and we have more and more absorption. So in other words, there is no light to emerge from the base of the cloud, and therefore no light means dark. That's why we see the bottom of the cloud dark. You will notice, look in the atmosphere, the thicker the cloud, the darker it is. And at some point it is so thick that you cannot even see the sun. You can also observe when you are flying. Let's say you have some very thick cloud, but you are here flying in the airplane. All clouds appear white. There is no dark cloud when you are flying. That's because light that is scattering from the top of the cloud is scattered in the Mie regime, and we once again have this situation where all colors are equally scattered, and consequently we see white clouds from the airplane. But if you would look those clouds from underneath, the base might appear as dark because they are so thick that all light is absorbed. Today's video described many beautiful phenomena. In the next video, we are going to discuss absorption of the light in the atmosphere, and until then, goodbye.